Oh, yeah. All right, let's go ahead and get started. Just a quick reminder, we have our Earth Day celebration on Monday. I know many of you have class, but if you can come out, it'd be great. So Earth Day, April 22nd from 11 a.m. to 2 p.m. So I'll be out there with my Chem 104 class, and there'll be local vendors and stuff showcasing their organization. And then lots of handouts at the front for you guys. Let's see. What happened? There were like 2 reduction potentials. Papers. Did y'all steal them? Oh no, I kept them. Not bad. Alright, I meant to put out another one. So I kind of got overexcited for some reason. So I had the stapled reduction potentials, and these are in alphabetical order, roughly. You can kind of see A, B, C, etc., ending with zinc. And I meant to put out a single sheet, so if you want to run and grab that, you'll want it for lab, but the single sheet is kind of more concise standard reduction potential data, so more common stuff. And then if you get really overexcited, just know that you can also find all the standard reduction potential data on Wikipedia. And that has an even more extensive list in case you're missing something on those reference sheets. And so I don't want to get too into it today since it's not our lecture topic, but I at least want to point out, so on this sheet, so the little sheet up in the corner, so you have like fluorine up there and ozone. So these are going to be things that are oxidized, so they want to be oxidized, right? Or your reducing agent, or sorry, not reducing, oxidizing agents. And then over here, these are things that are your reducing agents. So lithium, potassium, sodium, and they have a negative potential there. So that's at least how you can orient yourselves, but we can talk about this more in lab, and then of course, once we actually cover this in lecture. And then I put the homework out there as well. And so this week we're covering our thermodynamics and spontaneity chapter. And so let's start to get into it. And so now we kind of have to think back a little bit to thermodynamics and what we learned. When was this? First quarter or second quarter? I actually don't remember. When we did exothermic, endothermic reactions. So first quarter, all right, so now we really have to think back. So think back. So first quarter, right? So we had started introducing the subject of thermodynamics, and we said we studied, right, our change in enthalpy, and that was our Q, or basically, right, our heat exchanged. Oops, if I could spell. And we kind of summarized everything. So we said either we have these endothermic processes that, of course, right, need energy. And we said, right, we also have exothermic processes that release energy. And again, we were mainly looking at energy in the form of heat. So we were just looking at our heat being exchanged. And so now we want to get into spontaneity, into whether a process will occur. So this isn't telling us, right, whether something's going to occur or not. It's just telling us our heat exchange. And so now we are looking into, well, how do we know if a reaction goes? So that's the next part that we're asking now. Is, okay, we studied, right, whether things are endothermic, exothermic, but now, does this tell us whether something is going to go or not? And so the other thing of this, right, is this is not kinetics. And so what I mean by that is whether it goes or not has no bearing on how fast. And so we'll get into that right in a second. So we're just saying, is it going to go? It could be on a really long time scale. So that's, again, separately, right? Our kinetics, we always have to measure separately with our reaction. We have to have our experimental data for that. And so processes that occur are called spontaneous. And then we still can have a non-spontaneous process. It just means that it requires energy input. And we'll kind of, again, see this. And so this is where we're going to start to differentiate between endothermic, exothermic, and spontaneous, because again, it's not the same. And so spontaneity is determined by comparing our chemical potential energy of our system with the reaction with our free energy. So basically we're seeing, are we going from more ordered to more disordered? So what's going on? Are we becoming ordered, which, as you can imagine, right, making something more ordered is not favorable. Just kind of like cleaning your room, right? Your room always goes to disasters and chaos, and then you have to put energy in to put it back and put it back in order. And so now this is talking about, again, our thermodynamically favorable. So we said Well, if we have our system that has less potential energy, then our reaction is thermodynamically favorable. So again, this is referring to an exothermic reaction. But this does not give us, again, the complete process. And so let's look at a few examples. And so this is always given as a good indication of a spontaneous process, but one that is extremely slow. And so this is a more thermodynamically favored product, graphite, so it's the thermodynamic sink. And so again, this is why it's favorable, so over time, it would eventually convert to graphite. But again, right, it doesn't equal fast or slow, so the time scale of this reaction is extremely slow, so we would not observe it. So other things that we'll kind of look into, well, what about, can we have, right, a spontaneous endothermic process? And so the answer is yes. And a good example of this is your icy packs. And so they tend to be some sort of ammonium nitrate or ammonium chloride. I don't know why I wrote it out. And so what tends to happen is you dissolve it, so you break, right, your little pack, it dissolves, and of course, right, you start feeling it nice and cold, endothermic, so your body's supplying it energy, right? But that's still a process that is going to occur, and it happens as it dissolves and becomes disordered. And so that's kind of helps, drives that forward. So that's kind of where we're going, is again, we want to look at these processes. And so that's kind of, again, big picture where we're going is we're going to look at then the exchange of heat, so change in enthalpy, and then we'll introduce entropy. So those two factors are going to tell us whether a reaction will occur or not. And so reversibility, so any spontaneous process is irreversible because there's a net release of energy when it proceeds in that direction, and it only proceeds in one direction. So irreversible, and we can see that right with our rusting. So it becomes spontaneous and oxidizes over time. And right, we saw that a reversible process has to occur at equilibrium, and so there's no change in free energy. So that's where the difference is. So if a process is spontaneous in one direction, it's non-spontaneous in the other. So again, you can think back of your diamond going to graphite, right? It's never going to go graphite to diamond, at least not without doing something. So it's non-spontaneous. And so now we're kind of slowly getting there. So like we're seeing, usually these spontaneous systems and processes occur because, again, they release energy. So usually we're thinking about exothermic reactions, but again, we mentioned that's not always the case. And so we see that, so most spontaneous processes are exothermic, so from a system of high energy to our lower potential energy. So again, just thinking about basic thermodynamics, which one is more thermodynamically favorable. And so like we mentioned, though, there are a few spontaneous processes that proceed from a lower potential energy to a higher. So of course, those endothermic reactions, and again, we're getting to how we can quantify when this is going to occur and why it occurs. And so the key thing is entropy. And so now we're getting there. And so, okay, now there are two factors that we need to take into effect to tell us whether a reaction is going to occur or not. And so these are the enthalpy change and entropy change. And so again, enthalpy is what we covered before. So our first quarter, so just talking about our heat. So something feels cold, something feels hot. Our endothermic, exothermic reactions. And again, it gives the formal definition. So it's our pressure times volume, work energy. And so now we're introducing into this chapter entropy then. And so entropy is kind of defined as chaos. And it's the difference between the randomness of our reactants and their products. And so we'll get into what that all means and how to tell whether things are becoming more disordered or less disordered. And so this is kind of, again, a little recap for what we remember. And so our enthalpy change, we usually look at our reactions and we measure them in kilojoules per mole. And so, right, we said our reaction is generally exothermic if the bonds in the product are stronger than the bonds in the reactants. And so again, exothermic means energy is released. So we would calculate a negative change in enthalpy. And so again, just a reminder, and then we said something was endothermic. If our bonds were generally weaker, we could calculate the difference. And so again, our delta change in enthalpy was positive. And so, right, we kind of saw that. So this was generally considered favorable for our enthalpy change, right, to have an exothermic reaction. So that's generally favorable and occurs. And then endothermic reaction, they use this term unfavorable, but we're just saying, right, we just need some energy input. And again, it's not the full story here. And so now let's get into entropy. And so then entropy then is just defined as our thermodynamic function that increases as our number of energetically equivalent ways of arranging components increases. And so let's kind of think about what that means and how it gets complicated quickly. And so, right, we can start off with just thinking about a two-molecule system. So we have particles 1 and particles 2. And there's a stopcock here and another box. And so, right, we can open our stopcock, and then entropy tells us, right, how many ways we can put these little particles in. So 1 could be in the first box, 2 could come over here, right? We could also have 2 stays, 1 over here. And so that's just ways, again, assuming that we only have 1 particle. We could come up with other permutations as well where nothing happens. And of course, right, they both go over. So that's just, right, the number of ways that these 2 particles can exist in our system. So this is our entropy. And so it gets, again, pretty complicated pretty quickly with this W. And we can just see that if we go from 2 to 4, so 1, 2, 3, 4. So kind of repeating. So open up our stopcock, and now we start to get even more combinations. So maybe 1 and 2 stay, 3 and 4 leave. We'll do the opposite. Right, 1 and 2. Other permutations, what if 1 and 3 stay, 2 and 4. And so right now this is already out of control. So 1 and 3. I'll just kind of put right, etc. So you could keep going with combinations. We could do 1 and 4. And then, of course, put them in other permutations. What if there's only 1? What if there's 3? Right? So there's already a lot of different ways for these 4 particles to arrange themselves in 2 boxes. So just kind of comparing. And so now we're saying that our random systems require less energy than ordered systems, right? So it's more favorable to go to a random state is what we're saying. So this, and this is kind of what's being shown here, right? When we open the stopcock, these particles have a tendency to move around, to disperse, and be randomized. And again, trying to quantify all those combinations is extremely difficult and adds up very quickly. And so that, again, goes back to something that's ordered, has less energy. And so now let's look at some examples of entropy. And so salt dissolving in water. So that's one way to increase entropy. So we go from a solid state to now a free-flowing moving state. So, right, we've increased our entropy, so increased our disorder. So state changes are another example of how we can get either more order or more disorder. So evaporation, so you go from a liquid state to a gas state. Of course, right, gaseous particles are moving around, more randomized, so increased entropy there. And so, of course, again, now we want to start to quantify that. And so we have entropy defined as our Q over T here. So our entropy change or equivalence for this transformation is we can just take our entropy final minus entropy initial, so similar to what we did, right, for enthalpy. And so this is also equal to Q over our change in temperature, so T2 minus Q over T1. And then we have our Clausius form of our equation, so taking out Q. So our change in entropy is equal to Q times 1 over T2 minus 1 over T1. So let people write those down. And so now let's get back into our laws of thermodynamics. So right, first law of thermodynamics, we remember, so energy cannot be created or destroyed. So that was key, right, with our endothermic, exothermic reactions. The energy had to come from the surroundings or either go to the surroundings. And so that's shown here. So again, our total energy change in our universe is 0. And so energy was always exchanged between our system, which was our chemical reaction, and then everything else is our surroundings. And so now we kind of see this as well. So now it says the second law of thermodynamics says the total entropy change of the universe must be positive for a process to be spontaneous. And so entropy is always increasing, right? So our universe entropy is equal to system plus surroundings. And so if the process is reversible, then you should have no change in entropy, so just go back and forth. And then something that is irreversible, then your change in entropy is greater than 0. And so, right, we kind of have to balance this out. So we can't have, again, a 0 or negative change in entropy overall. So if the entropy of our system decreases, we basically have to kind of pay that price somewhere else. So the entropy of our surroundings must increase by a larger amount. And so again, when our system entropy is negative, then our surroundings must be positive and big for a spontaneous process. And so again, entropy change is favorable when the result is a more random system. So that gives us a positive change in entropy, so that's favorable. And so now we've kind of seen a few examples. And so what we've seen are changes that increase entropy are as follows. So we have reactions whose products are in a more random state. So usually thinking about our state of matter. So obviously your solid is more ordered than your liquid, and your liquid more ordered than your gas. This one is also really important. So reactions that have larger number of product molecules than reactant molecules, so especially examining those gas phase reactions. And so if you go to more products, that's more disorder, so more potential states for all those products to be in. And then increasing your temperature, so that is also going to increase your entropy. And then anything disassociating, so that's also increasing entropy. All right, so now we're looking, here's our surroundings. So this is just kind of, our recap here. So our two systems, so there's no heat exchange between our environment and our system here. So now we're just measuring our heat flow. And so looking at our system, so we have our change in entropy, so this is just total change in entropy has to be equal to, let me zoom in, our entropy 1 plus entropy 2 from our two systems. And so that has to be greater than our heat. And so Q2 has to be equal to our negative Q1. So again, assuming this is an insulator, heat can only be exchanged between these two compartments. And so that's again how we got this equation. So here's kind of our re-derivation from before. And so now we can write, so our change in entropy has to be greater than our heat exchange between our two temperatures. And then we end up with this equation. And so W stands for work. And so this equation is giving us, how much work can be performed based on our temperature difference. All right, so then slowly getting into all the quantification of this. So again, like we said, the change in heat loss is equal to what our surroundings gain. So if we lost heat in our system, our surroundings gained it. And then we said, okay, well, our entropy change is also proportional to this. So we're slowly getting there. And so again, we're left with this relationship. And so this is key, so at our level, we're just looking at constant pressure and temperature so that we can just quantify our work. And so then our relationship is that our change in entropy for our surroundings is equal to our negative change in enthalpy of our system over temperature. Again, we'll keep looking at other equations. And so let's just kind of practice for a little bit. So take a few minutes to look at this and just figure out, is entropy increasing? So is our system becoming more disordered, or is entropy decreasing? So what do we think the sign is for this first process? So we're going from H2O gas to H2O liquid. So is entropy increasing or decreasing? So decreasing, right? So we go from gas to liquid, so entropy negative. What about B? So solid carbon dioxide sublimes. So increasing, excellent, and of course, right, sublimes just means goes from our gas to solid state. And then what about this last one? What do we think? So increasing, and why do we say that? So more molecules of gas, so excellent. So right, we started with 2 molecules of gas. Now we have 1, 2, 3. So 2 moles to 3 moles. So yes, our 3 moles can be arranged more ways. So excellent. And so let's look at other ways to quantify our entropy. And so, right, we've been using all these relationships, but now we kind of want to get into what we'll call, right, our kind of standard enthalpies, or entropies, sorry. And this kind of goes back to our standard enthalpy table, right? So everything kind of had that standard heat of formation. You remember that from our enthalpy chapter. And so now we need to do the same thing for entropy, right? So we have to have our standard entropy for all our molecules. And so how we get there is, well, we got to define what 0 is. And so that's what this is. So absolute entropy. And so now it's saying the absolute entropy of a substance is the amount of energy it has due to dispersion of energy through its particles. And so then what is a 0 state? Well, what if we have a perfect crystal at 0 degrees Kelvin, so absolutely no motion. And so, right, if we had a perfect crystal at absolute 0, then its entropy would be 0 joules per mole Kelvin. And so notice the units, right, so it's joules per mole Kelvin, so it's temperature dependent. And so therefore, every substance that is not a perfect crystal at absolute 0 has some entropy. So, right, everything's going to have some entropy. And so we'll see that, right? So therefore, the absolute entropy of substances is always positive. By perfect, I'm assuming they're meaning like no imperfections, so like no, what it's called is sometimes you get a crystal and then it crystallizes with disorder, so they're not all in the same like place, if that makes sense. So like what we've kind of talked about before with our crystal structures, you know, something crystallizes, whatever, in some happy arrangement. And this is like an extreme oversimplification. So like a better example of what actually happens, and I've had this happen, is like if you get a solvent molecule that gets in there, so like hexane, so 1, 2, 3, 4, 5, 6, and then sometimes it can do kind of like weird things and crystallize in different ways. Yeah.
And so we should assume that like any substance which is a crystal at 0 Kelvin is not perfect, and therefore thus have absolute entropy.
Yeah, well, and usually, right, we're not even going to be at absolute 0. So that's kind of the other thing. It's like, you know, absolute 0 is just theoretical, but yeah, so there's always something. But yeah, it refers to kind of disorder, any impurities. And so this, if you had like weird disorder, it would just mean like the hexane is not in the exact same spot. So maybe there's some like rotational issue or something, or it's not like the perfect repeating unit over and over. Any other sort of like substitutions like that. So when we get into like doping later, like that's also what that could be. All right, does that make sense? so far. And so now we get to our standard state, again, just like we saw with enthalpy. And so for a gas, this is going to be for 1 atm. For a solid or liquid, and then it's going to be in its purest stable form at 1 atm and 25 degrees Celsius. And then solutions will be in 1 molar. And so again, right, when we're looking at these values, these are these standard conditions. So of course, you know, if you deviate from those standard conditions, then maybe your theoretical entropy or where we're going gives, that's why they may not match up. So just kind of keep that in mind, that it has to be under these standard conditions. And so now we're getting at, so when our process in which our final condition is more random, then right, we're going to see that our change in our entropy is positive. So we kind of could predict that, right, like you saw with the states going from solid to liquid, solid to gas. And entropy change is favorable for that process to be spontaneous. So usually that helps, right, drive your reaction forward. So kind of thinking of, again, those ice packs. So how does it work? Well, it has your entropy driving it forward. So going to more chaos, so more favorable. And then, of course, if we had our final condition being more ordered, then our change in entropy is negative. And of course, that's unfavorable, but not saying that it can't occur, just that it's only going to occur under certain conditions. And so, of course, right, how can we figure out what conditions those are under? Well, that's where we're slowly marching to. And so, again, to get there, we have our standard absolute entropies to kind of help us. And so, again, our little circle here indicates standard state conditions. So kind of pointing right at that little circle. So standard state, extensive physical property, so it depends on amount. And entropies are for 1 mole of substance at, again, 298 Kelvin, so 25 degrees Celsius for a particular state, allotrope. And so we can see what that means. But, right, you remember allotropes. So what are allotropes again? So one element, just different arrangements. So what's like a common example? Yeah. So all the carbons, right? So you got to pay attention. So they would all have separate entropies. So diamond versus graphene. So just watch that. And then particular complexity, molar mass, and how much it's dissolved. And so now this brings us to at least, right, some standard entropies that we could find in any reference page. So this probably is in the back of your textbook, assuming that they still have entropies somewhere in there. I think if we click this link, oh no, this link is broken now. Let me see. What happened? Well, that's frustrating. I'm sure Wikipedia has them. Oh, good old Wikipedia. Oh, come on. Where are all the values? Yes. That better not be a dead link. No. All right, I'll have to look for some better standard entropy internet values. I don't know what happened to them. But basically, we can see, okay, we have our substance. It tells us what state it's in. And then your standard entropy should be in joules per Kelvin mole. So again, right, it depends on amount. It's what it's saying, and it depends on our temperature of our reaction.
Would you prefer us to use values from a specific place, like if the other house used the sheet that you handed out, that table in the textbook?
Well, the sheet I handed out was for yeah, reduction potential. So I didn't actually hand out an entropy sheet. I don't really care where you get the values from. They should be the same. I was just trying to find a more extensive list. Might have to get on NIST. So this is just another state, but it should have pretty similar values no matter where you look. And right, this one, for example, has enthalpy and entropy, so this could be a convenient chart. Maybe I'll print it since I need to print you something. And so again, just kind of taking it in. So here's carbon solid. And notice, right, that's graphite over here. So pretty low entropy for graphite. What other ones are interesting to look at? And so this mentions, right, this is calcite, so this is a particular structure. What else is interesting? So of course, water, right, different entropies based on its state, so gas, liquid. Surprised they don't have solid water. All right, so yeah, it doesn't matter where you look at these values, they should be relatively similar. You probably just want to make sure you're in joules in case you find one with electron volts or something weird. And so now we can at least kind of compare. So we can look at our chart, and just like we saw, oh yeah, right, our gas has a higher entropy than our liquid. That makes sense, that's what we expect. And so here are some, again, just kind of more values. So this is from another textbook, so just comparing our gases. So you can see kind of your more atoms tends to equal more entropy. So right, we only have 2, although that's pretty small. Yeah, and then compared to like our 6. And so it's kind of size dependent and however many atom dependent. Then our liquids. And so solids we can compare, so it also depends on how they pack. So, right, these would depend on their crystal structures. Of course, they tend to pack in a certain way. And so, right, molar mass, like we're seeing, again, this is just in general, larger the molar mass, the larger their entropy tends to be. And so our allotropes, again, it just depends on who's more structured. So diamond has a 2.4 entropy versus 5.7 for graphite. So graphite's less constrained, so a little bit more entropy. It's still both pretty low.
Okay, I have a question. If entropy is based on ways things can be arranged, why would any one atom have any more or less entropy than any other one? Like, for example, with an element.
Well, like they were kind of stating here, right? So it depends also on like the energy levels, so how many electrons, right? So that's also playing into it. So that goes back to like the mass argument. Does that make sense? So that's like comparing, you know, like,
It's got more electrons. That makes sense.
yeah. So just kind of comparing, right, iron and nickel. So like nickel should have more entropy because of that. Again, just slightly. So our molecular weight. All right, so now we get into quantifying, although this might be a good time for a break, just thinking about it. So let's take a little break, and then we'll get into the math of Gibbs. Yeah. But let's meet back at like 11:55 or so, take a little break, and then we'll get into Gibbs. Are you chasing him away? He's just trying to eat a sandwich.
Yeah. They're like, "You're gonna eat your turkey sandwich." Carmen, I didn't realize you were here.
Sorry. I totally just took it. No, it's good. You're good. Really? Yeah. Work and life. I didn't have
And now I'm not going to feel this. I just absolutely need to screw. Thursday. No, you don't.
I have no, I had a question going around on Tuesday when I asked you, like, about setting it, like, it is Tuesday, I'm like, I don't know what it is. Yeah, it's mildly unfortunate because those are usually my days too. Slightly more stressed about it, but if you would have been, I'm alive. Very, I'm anxious today. It doesn't bother me.
Calm down.
Thanks, appreciate it.
Just hearing it.
I'm like, took me back to high school, jeez, man.
Just don't get anxious. I'm just sorry. Sorry, I'm trying to.
I wish that would work. Imagine if all the time people like said just call it out.
Just I'm just kidding.
Well, yeah, the dog wasn't trying to attack her, it redirected on her, but it was a bad move. There was no, I think the dog grabbed onto her stomach and then like shook, so it was like, that's why I said. Yeah, so I'm like, yeah, it's been, according to her, a month and a week. She's counting the days.
Like, did it actually bite her? Like,
It was a bite, because what the redirecting is like,
so mad.
them being frustrated with something else, and then you're the closest thing to
Really?
that.
Yeah.
I don't know if I'm patient enough for that. Like, I get why the dog would like, but I'd be like, you middle school.
Okay.
Like, I don't
No,
know.
she's, well,
You're getting
what happened?
I'd be like, oh my gosh.
So, well, it's a very traumatic experience, and so she's basically, like, she's struggling with it, and then like, because it means like she's been getting anxious at things she doesn't want. But she wants to push it through, like, feels like, she wants to hang out with the dogs and be like, with the dog, but it's like spiking her anxiety to like, like really high level and talk about it. You gotta take your time. There's a reason that you're still struggling with it. A month may seem like a lot from one perspective, but from the perspective of your body experience, it's not how long.
At least.
she's actually like, she is really sweet, she just really doesn't like other dogs, and she was reacting to a different dog, but, yeah.
It's like, it's like her dog. She's really good, but she's really good when you like take her places or houses are, but she's so defensive of the house. People like come in, it's like, our backyard, with a rostrum fence. And there's a space in it, and so these little dogs, like, those one specific dog would come up and bark, like, and yap at our dogs, and Cookie literally, like, when she gets locked on and gets like, kind of like, she's part grateful, she gets like kind of like zone out, like I'm not listening to anyone else, I am like, I'm gonna kill this dog, like, yeah, and you have to like really try and stab her out. Literally, it's like she goes into like defense mode, like I'm going to take this thing out.
My dog is like that too, but he's like a little guy, so like he's really endangered. That's his size. But like he's just like the same way like he's like I'm good.
Yeah.
Like that's
Yeah.
really
She's like 45 pounds, so she's strong, so I think if she went after someone, it's not like a chihuahua coming at you. It's like, you know, if a mix coming at you.
Chihuahuas are the worst, man.
Yeah.
They are. Well, because you're not as prepared for Chihuahua biting. Like you're mentally, you're like talking to a big dog. You're like aware it's a big dog. You're not aware of Chihuahua until they bite you.
They're so mean.
and they're just defensive.
We're almost 50 this weekend.
Chihuahuas, yeah, they're like the most common dog bite.
Yeah. Oh yeah.
Well, not all, but.
Freaking cheese man, but no. Well, they had him tiered wrong. They had him as a tier 1, and he was not a tier 1. So it means tier 1 means anybody can hang out with them, friendly dog, not a problem. This dog was at least a tier 2.
Cheese is at least tier 2.
Well, no, because I went in, I saw that it was tier 1, I'm like, okay, I don't know this dog, but probably be okay. So I went in kind of cautious, like, normal, like fine, casual, until he like looked at me and and came out.
He's more
I'm
like
like, no.
Jack than
You gotta know it really quick. I don't. I just wanted to picture Betty. I have never been chased. Never like in a vicious way. Shadow would chase me, but that's fine. Never in a vicious way. I got actually a chihuahua because my mom had a chihuahua that shouldn't have been in the home with me, basically because I was a toddler at the time. And
For a toddler versus chihuahua.
a chihuahua who had been abused, who had like came from a bad home. So it should not have been.
Not a bit around kids. That's not, most chihuahuas,
Well,
like
It wasn't
kids.
when it got
It bit me in the eye.
In the eye?
Yeah, because I'd get too close to it.
actually big.
Yeah.
What? Well, they're a little toddler.
Yeah, it's
Oh,
weak, it's easy.
It's gonna go.
It's an easy target.
Two.
Just because they're eager, they're like easier to care for. Yeah, no, we get 20, we get like 25 small dogs every other week, or I can't remember the exact. We get them in the winter, and then they're gone, and there's big dogs in there for
Were you very sore after the 10-mile bike, Carmen?
Dude, yeah, I used to walk on my last year, but I stopped walking when they were on their own path.
I had to go to work. Kind of walking around though, kind of like gets the sweat yourself.
I did not hit that.
After the 10 mile. Well, I mean, it wasn't planned to be like almost 10 miles.
Did you run this weekend or something?
What?
Did you do the pear blossom this weekend?
No, we went hiking. I went hiking to Rock.
Oh, nice.
It was supposed to be short, but then me and Carmen decided to go and explore and ended up like
like over and down.
Oh,
Well, I should have realized it was gonna turn into private property. There wasn't like a second trail that you could like back around. I was curious if there was one, but no, it just turns into private property, so.
At least you have your answer.
that sucks.
I cannot understand my life how.
Get off the board.
Oh, I usually get off at 5, but I'm exhausted after that.
That's way late.
Well, no, I didn't, well, I do, it's all physical labor, so all day I'm moving around and watching things. It's not, it's, go home and I don't even wanna do homework, I wanna sleep. Like sometimes I'm like, I got video games. But not. I can't do calculus on it. Well, I've heard it. Monday's very much.
Well, I mean, here's the thing, Ashley's gonna look a lot like 5.
I get a lot of Mondays, because our Mondays are like, I don't know, so.
It doesn't change the
That's why I have a lot of time.
It does not.
Well, not really.
Well, so
5
after
sounds
3
good.
is after Saturday and Sunday.
I'm gonna make fun of the hard work.
Technically Friday, and then they're all going to stop. So Monday afternoon.
There's nothing cooler about these, when you get these mixed up.
Are we all back from break?
Hopefully theoretically.
Hopefully theoretically. All right, let's get back into it. So I did hand out at least some standard enthalpies and entropies for y'all. So again, just note that the enthalpy is in kilojoules and entropy is in joules. So that will be more relevant once we actually get into math and plugging in numbers. And so before we dive into the math, we want to at least kind of predict under which conditions we'll have a spontaneous reaction. And so now this is kind of putting together everything we were kind of saying before together. And so now we're going to quantify everything with our Gibbs free energy. So Gibbs free energy is basically energy that is available to do work. And so this is combining, right, our enthalpy and entropy conditions. And so again, let's go through the verbal part, and then we'll get into the math. And the key part is, of course, highlight this. So a process will be spontaneous when delta G is negative. So we're looking for a negative delta G. And so we have available Gibbs free energy under the following conditions. And so as you might imagine, if you have our delta H is negative, so right, our exothermic reaction, and then our change in entropy is positive, so both exothermic and more randomized, that's kind of like 2 checks, check, check. So this is going to be spontaneous. And then we have other conditions, and again, this is where the math will get into the details. But we can also have, so what if we have a large change in enthalpy, so right, an exothermic reaction. Exothermic, so it's negative and large. And then in this case, right, we could have maybe a small change in entropy that is negative, so becoming more ordered, right? So now our entropy is becoming more ordered, but as long as it's small enough, right, that this is large enough, then it's still positive, so, or sorry, still spontaneous. So delta G is still negative under these conditions. And we might also have this last condition, so again, now we have an endothermic reaction, so our change in enthalpy is positive but small, and then our change in entropy is positive and large. And so thinking about maybe our dissolving system, so as long as we have a large enough change in entropy, so going again from ordered to more disordered, that's going to help drive this reaction and help drive that endothermic reaction. Or possibly happening under high temperature conditions with this situation. And you can imagine, right, we'll quantify this high temperature when a process becomes spontaneous or not at some point. And so these are the conditions that we expect that delta G would be positive. So non-spontaneous, right, not occur. Non-spon. So it does not occur under these conditions. And again, perhaps you can alter the conditions and make it spontaneous, but again, it depends. And so we expect delta G to be positive when we have delta H is negative, so exothermic reaction, and a small delta H, so right, and then it's becoming more ordered and it's large, right? So basically, even though it's exothermic, because this system is becoming so disordered, this can't, right, overcome that. And so this would also happen at high temperatures with this spontaneous, right? So again, spontaneity is goes along with temperature, so at those high temperature conditions. Oops. Delta G will also be positive if our change in enthalpy is positive, so right, our endothermic reaction. But then if our change in entropy is also small, right, then it's not going to occur. So basically we're saying even though, right, our system is becoming more disordered, it's not enough, right? It's too small of a change to overcome this endothermic process. And this might also happen at a low temperature. So again, right, not enough entropy, not enough disorder at that low temperature to overcome that endothermic reaction. And then this would be our condition where it is never spontaneous. So if we have a system where our change in enthalpy is positive, so again, right, endothermic reaction, and then we're becoming more ordered. And so this would not occur. So if it's endothermic and more ordered, then that will not occur. And so now we can also kind of compare our Gibbs free energy. And so notice, right, our last kind of point there was if our delta G is 0, then we have a reaction at equilibrium. So I don't think we'll look at that too much, but just keep that in mind. And so here's again kind of where you can start engineering your reaction. And so we're looking at our free energy, so our Gibbs free energy, and comparing our Q and our K, so right, our equilibrium mixture, kind of seeing where we are. So at this point, let's just orient ourselves. We're at our equilibrium conditions, right, where we said our equilibrium is equal to our snapshot. And so we can also have, right, our Gibbs free energy can tell us which direction it's going to go. So it's going to go towards equilibrium, and so in this case, right, it's spontaneous in both directions. So going towards our equilibrium, so of course, right, our Q was less than K, so less products than reactants. And we have, right, our pure N2H2 labeled over here with our free energy, and then it's going to go towards our equilibrium. So same thing with this system. So pure ammonia, we have Gibbs free energy available, and then going towards equilibrium. And so now we're getting into more equations. And so this is kind of, our key one is here. And so basically, right, we had said that our energy available then is equal to our change in temperature times our entropy of our universe, so the negative of that. And so this is equal to then our change in enthalpy minus temperature times our entropy change. And so now we've just defined what this is. So again, we use G, so Gibbs free energy is again the maximum amount of work energy that is released. So right, it's whatever energy that's available to do work. And so sometimes it can be thought of chemical potential. I usually just think of that as kind of, you know, our enthalpy plus entropy positions and, right, the overall sum of that and what, again, what energy is available. And so this all kind of makes sense too, looking at our units of what we're given, right? We said entropy is temperature dependent, so that's why it depends on the temperature that the reaction is occurring at. And again, right, you see that reflected in the units of entropy. And then, of course, we have our enthalpy over there. So if you just need to remind yourself, so enthalpy versus entropy. And since we said, right, our change in entropy of our universe determines what's spontaneous, then our delta G can also tell us. So this is, again, what we use to quantify and talk about whether reactions are going to occur or not. It's always that delta G. And so this is another kind of a cheat sheet summary of our different conditions and what we can expect. So it's kind of a summary of these words here. So let's go through it again, just so we feel good about this. And so looking at this, right, we have our change in enthalpy is negative. So that's an exothermic reaction, and then entropy is increasing. And so, right, this is telling us that at low temperature, this is going to be spontaneous. And then it's also going to be spontaneous at high temperature with these conditions, and you can kind of think about plugging it into that equation, right? So you have, let's just rewrite it as well. So delta G, right, equals our change in enthalpy minus temperature times change in entropy. And so now we can plug these in. Well, if our enthalpy is always negative, and then our entropy is positive, right? It doesn't matter what the temperature is, spontaneous at all temperatures. You can kind of see that. And so here's just an example of a process that would follow that. So our dissociation of N2O to nitrogen and oxygen. So we could calculate this, right, with our standard enthalpies. So we could figure out that our enthalpy is negative, so exothermic reaction. We could also figure out, right, our change in entropy, so we could quantify that. We can also just kind of see quickly, will we go from 2 moles to 3 moles? So that's a good indication that our spontaneity is increasing. And then if we look at our next scenario, again, we can kind of plug in these numbers. Well, let's kind of break this down. So now if we have an endothermic reaction, so now this is positive, but then our entropy decreasing, so right, minus here. And so now we can see, right, well, we're always going to have a positive delta G, right, because you're taking a negative, always multiplying it, so it's always going to end up being, if you plug it in, positive, right, plus a positive. And so that's where you can tell, oh, this is non-spontaneous at all temperatures. Does that make sense for that one? And so that would be, right, our oxygen 3 oxygen molecules combining to ozone. But I think we've looked at this before, that this needs to be catalyzed in the atmosphere for this to occur. Otherwise, right, we're seeing that it's non-spontaneous. Yeah, that's a good point. We wouldn't have any oxygen to breathe. So, I mean, seeing the physical relevance is always funny. And so then, right, our next conditions. So now we're saying, right, exothermic reaction again. And now this time, right, becoming more ordered. So we can look at our example, like water freezing. And so now we could, again, kind of plug in some values. And so this is what you might expect as well. And, right, you've seen it happen at low temperatures. And so at low temperatures, if negative, negative. So, right, this is negative, our enthalpy. But we can't have, right, this become too high since it's becoming disordered. So that becomes a positive, right? So it's basically, if we do the math, negative plus a positive. So we don't want this entropy, right, to get too large, that value. And so that's why it says, well, it's non-spontaneous at high temperatures, so we could see that mathematically, where then, right, our change in G would be positive. And so, yes, right, we know at low temperatures that this does happen. You've seen it in your fridge or freezer. And then our last condition, and so looking at, again, an endothermic reaction that is becoming more disordered. And so this would be like liquid water turning into gas. And so now we have this, right, positive minus some value. And so, right, we want this to be large enough. And so that's kind of what we see here. So, right, this process is non-spontaneous at low temperatures. So basically, we kind of see that mathematically that, oh, if this number, right, we need a large negative number to add to this, right, to get our negative delta G. So that process is spontaneous at high temperatures. So again, you see that high temperature times this positive disordered, so that gives you large negative value to overcome that endothermic process. So does that kind of make sense? So this is a good summary of, again, all the words that we looked at before. And again, kind of plugging it in quickly to this equation kind of helps us get an idea. All right. And so now let's look at this next one. And luckily, we don't have to do too much. And so what I mean by that is eventually you'll have to calculate, right, your change in enthalpy and change in entropy of a system potentially to plug in to your Gibbs free energy. And so we'll start off with this warm up though. And so they give it to us. And I'll let you start it off. So we're looking at this decomposition of carbon tetrachloride to give us graphite and chlorine gas. And so they've done the work for us, and they've given us a change in enthalpy of 95.7 kilojoules. And then our change in entropy for this reaction is 142.2 joules per Kelvin. And so let's just start with the first part. So calculate your delta G at 25 degrees Celsius. So what do we get for our change in Gibbs free energy, or delta G? And what were some key things that we had to do? So what do we have to do for temperature? So change it to Kelvin, and then you might as well just stay in kilojoules, so we can plug in our 95.7, but then, so we'll do 298 times, and then don't forget to convert this to kilojoules, unless, again, you want to convert this to joules, but numbers get kind of large. So then we should have something like this. And then, so what did you get for your G then when you plugged it in? So then you're in joules. Oh, so 53,000 joules or 53 kilojoules. And so is that spontaneous? So nope, not spontaneous. So write positive value, not spontaneous. And so now we're going to do what I said we were going to do. And so now, right, if it's not spontaneous at this temperature, which we said it wasn't, determine at what temperature, if any, the reaction is spontaneous. So see if you can set that up. So what did we do for part B? At least, how do we get started? How do we set it up? Excellent. So that sounds good. So right, we can set it to 0. That's where the point is. And so now we just have to plug everything back in again. And like you said, use a variable for our temperature, X. And then we'll get our answer in Kelvin. And so now algebra. If I could punch things in appropriately. And that should be positive since I didn't plug in a negative. So I got 672 Kelvin. Is that what other people? So 672 Kelvin, it starts to become spontaneous. Or so if we want to put it back in Celsius, so about 399 or 400 Celsius. Excellent. So right, we have to have a high temperature for this reaction then to be spontaneous. Oops. Questions about that example? All right, so then the last bit of this chapter, which we kind of flew through this chapter, but probably do a lot of practice on Thursday. And so now we want to relate our change in free energy and, of course, our good old K, equilibrium. And so, right, we had said, well, our Gibbs free energy of our reaction is 0 at equilibrium. And so we also have this relationship here. And so we have our change in Gibbs free energy is equal to negative RT times our natural log of K. And so this is going to be our other R, right? So R is at 8.314 joules, mole, Kelvin. And so, of course, again, we'll look at this relationship. And so we'll find, of course, if K is less than 1, then our Gibbs is positive, and the reaction is spontaneous in the reverse direction. And then if K is greater than 1, so more products, right, our Gibbs is negative, and the reaction is spontaneous in the forward direction. And if we're at equilibrium, of course, K is 1 and G is 0. And so again, this summary of that. And so we have kind of other relationships as well with our comparing our snapshot Q and P. So right, we're going back to our pressure. And so we could either be in concentration, and so right, this is just our natural log of Q over C, so this is in our concentration, or this could also apply to our pressures, right? So similar. And so our units of concentration cancel out, right, just like we saw before, and same thing for, right, our equilibrium constant for pressure. And so now we can, from this we can see, right, so if our Q over our our equilibrium constant is greater than 1, so right, too many, we're past our equilibrium point, then this is going to be greater than 0, so our Gibbs free energy, and so this is positive, right, non-spontaneous. And then, right, like we saw before, so if our Q is less than our equilibrium point, right, then we're saying, well, the reaction still has to occur. So this will be negative. So our delta G is negative, so spontaneous, so it's going to occur in the forward direction. And again, right, once we're at, if they're equal to each other, we're at equilibrium. All right, so now we're looking at this dissociation reaction. And so let's just start off with seeing if you can calculate the equilibrium constant. And so they gave us our gives free energies for these two. And so you might have to calculate, right, your delta G of your reaction then. So products minus reactants, kind of like before, right, where you sum up all your products minus sum up all your reactants. So this is just another way to get to delta G. So see if you can try that. All right, let's at least start hearing what we did. So again, first part was we just had to find our delta G of our reaction. And so the tricky part, the only tricky part was you had a 2 here for your NO2. And so if we take products minus reactants, then we have 51.3 for NO2 times 2 of it, right, because we have to sum all of it. And then minus our reactants, and we only had the N2O4, so minus 99.8, and it should be in kilojoules. So then I ended up with 2.8 for our change in G, so 2.8 kilojoules. So is that what other people got? And so now, from there, we can plug it into our next relationship. So it asks for our equilibrium constant. So we said delta G was equal to negative RT over ln K. So there's K, right, what we're looking for. And so now we can plug our numbers in. So 2.8, and I'll just write kilojoules, just so we're clear, because I'm going to have to change it, is equal to negative R. And so here's my problem, 8.314. This is in joules. Let's go ahead and change this to joules as well. Or maybe I should have crossed that out. So 2,800 joules, just so we have matching units, times our T, I forgot what temperature we're at, so 298. So plug that in, it's already in Kelvin. That matches up. And so now times ln of K. So do we make it here at least, maybe? So it sounds like yes. And so now just algebra at this point, so let's do it. So divided by, let me 8.314 times 298. So we get something like this. So negative 1.13 is equal to ln k. And then ln is natural log, so e. So we could take everything to the e power. So that gives us k, and then e to this. If I can find my e, and make sure you're using the correct e. So different e's for different situations. So point. So this then is our k, and how many sig figs do we have? About 3. So 0.323 is our k for equilibrium constant. Questions about this one here? And so now we can get into kind of other forms of these equations. And so, right, we have this relationship, so we can either calculate our delta G from our enthalpy and our entropy like we saw, and then we can relate it to our equilibrium constant. And so now we get another form of the equation, and I think this will be relevant for lab later. I don't remember which lab, at least it seems like it is, if I'm recalling correctly. And so then we can show that we can relate our equilibrium constant, so take the natural log of that, and then it's equal to our enthalpy of our reaction over RT. So you can see, right, how the RT factor was pulled out. So divide by T there, and then plus our change in entropy over R. And so this is why I was thinking it'd be relevant to lab, even if you don't do it in our lab, then maybe another time. And so, right, this equation gives us our y equals mx plus b form. So our 1 over t is our x. And so, right, we can graph our natural log of k versus inverse t, and that gives us a straight line. And conveniently, right, your slope then is your change in enthalpy over your R. So R, again, is just that gas constant, just so people don't forget. And then your y-intercept ends up just being your entropy over R. So that can be convenient, again, given the right situation. And so this also leads us to other forms. So then, right, you have your, and these are all just different forms of this, right? So then you have your Van Hoff equation. Maybe you did this in another lab. And so this is how you got your relationship. So our natural log of K1 over K2, so comparing those reactions is then equal to our delta H of our reaction over R times our T1 minus T1 over T1 times T2. So that's one form. Or the pressure-related one. So this is for pressure or gases. And you have the Clausius-Clapeyron equation, if I could spell. And so this is another form of it. So now your natural log of your pressure, so P1 over P2 is equal to our delta H over R, again over T1, T2 minus T1 over T1 times T2. So those are just other equations that come up.
We had a very similar equation with geometry.
Yeah, they're all pretty similar as well because it's kind of related. All right, we're kind of ahead in lecture. Let me give me 1 second. I need to pull some more practice problems for y'all. Or we could look at your homework. Let's see. I'm gonna look at your homework. Let's see what is. Your homework actually doesn't look that bad. But you should do it. No, let's try 9. I have other practice too, but apparently I didn't put it in. So let's just start off with 9. Yeah, I'm trying to find the harder problems. Why don't you walk us through our setup then? So what equation did you pick?
Gives free energy at standard conditions is equal to -RT natural log.
Excellent. And so, right, they gave us our K, right? So this is our K that we can plug in.
Yeah, and I assume it's at 298 degrees Kelvin.
Yeah, so that's a good assumption, right? So they didn't tell us, but 25 is good to assume. And so I guess we're ready to plug it in. So negative 8.314 times 298 times times the natural log of 1.4 times 10 to the negative 8th. And so you can either yell at me while I punch this in, or so that's what I've punched in for Gibbs. So is this what other people got? So pretty close. And so this is in joules though, so I'm going to divide by 1,000 just because I like kilojoules and my eyes get squirrely. So 44.8 kilojoules per mole is our delta G here. And of course, right, we can say that that's not spontaneous. Oh, yeah. Yeah. Although, because if you take the natural log, yeah, so that is kind of weird. So I think 3 sig figs is okay, but I probably wouldn't fault you if you put 2, thinking that. Do you have a question or just? Too many Gibbs free energy calculations. All right, what else? Let's try 8 then. What do we get for 8? So we can use our same formula. Watch your units, right? We're in kilojoules over here. And then it told us we're at 25, so I'm just plugging things in. So then for 8, this is what I get for the equilibrium constant. So about 3.4 times 10 to the 17th with that one. Do we all get that? Huh. Oh, that's funny. Do you use 298? Ah. That 0.15, nice. Yeah, so about 3.4 or so times 10 to the 17th. Let's try one more. And so let's look at number 5, just because this is one of those ones that I call it's like a little tedious, right? Because we have to look up basically our H values from our table, our entropy values, and I would use those to calculate your delta G values. So I'll let you kind of look at that, and then we can kind of talk through more how that process works. So I'll start kind of going through it just because we're slowly running out of time, so don't feel bad if you're still working on it. But basically, right, we just want to look up, and conveniently, I think they're on the sheet I gave y'all. And so the best practice is to find, right, your standard enthalpy values and standard entropy values from our chart. And then, right, we can use that to calculate our delta G from our other formula. And so just from the chart, so I'm just looking at this chart, so H2, and again, conveniently, we have both enthalpy and entropy. So we can see it's 0 for our enthalpy, and then entropy is 130.6. And again, right now that this one is in kilojoules, this is in joules. And so now I'll do the same for oxygen. So it should be 0 from what we remember from standard enthalpy. I'm not blind here. So oxygen, yes, is 0. And then entropy, make sure we're in the right state, gas is about 205. And you might have slightly different numbers, again, depending what you use. Then water, make sure we're in the liquid state. So then it's enthalpy, negative 285.8 roughly. And then its entropy is 69.9, or maybe 70 in the book or something. And so then we can calculate, right, our change in enthalpy from the reaction, so products minus reactants. And so products are our water, so let me do enthalpy first. So negative 285.8 times 2, and then we'll minus 0. And so that gives us, right, negative 570 for a change in enthalpy, so exothermic reaction. And then that makes sense, right, gas to liquid, so we should be losing heat. Then we can calculate our change in entropy. So again, same thing, 69.9 times 2 minus our reactant, so minus 205. And minus 130.6, and so about, oh, you're right, good catch. And so minus 130, sorry about that. So does that look better? So then we should have had a change in entropy. Again, don't forget to multiply by 2, unlike me. So negative 326.4, and that was joules. And so best practice, we can use those numbers to plug it into our delta G. So equals delta H minus T delta S. And we're at 25, so again, just calculating. And I'm going to put this in joules. Maybe I should have gone the other way. I changed my mind. So I'll put this to kilojoules. Doesn't matter which one you want. 298 times, this will be a plus. So negative 570 plus, right, since this is negative, so 298 times 0.3264. And so then we get our delta G of negative 472. And that was in kilojoules per mole. And so I think we're already over time. But right, then you can go ahead and calculate what temperature it'll be non-spontaneous. So setting that delta G equal to 0. So we can finish this up on Thursday if y'all are interested. And so Thursday we'll just do kind of more practice. I have some harder practice maybe that I pulled from another textbook, so I'll move that over to our current notes and we'll do that on Thursday. All right, I will see y'all in lab otherwise, and of course you can bug me, ask me questions. Oh, yeah, you can. I forgot. And then as y'all are running out the door, so great research opportunity. So this is with the OSU Extension Center, and you can do all this like plant research. And so highly recommend it. One of my former students is currently in this program, and I just hear amazing things about her. So I highly encourage y'all, if you're interested, you know, look into this. I don't have all the details. This is all I have. But I think you could work for them. You can see what also kind of summer opportunities they have. So highly recommend. All right, let me print out my food.
The other one's also a lot smaller. It's so just like, oh, it's actually just like that. So
you feeling like you're getting this back? It's like some sort of summer internship.
Yeah. Some sort of thing that cool people probably.
Also, you suggest it to.
Yeah, that's why I suggested it to you.
Yeah, weirdo.
I'll probably see you then,
Probably, maybe.
unless it takes me about 30 minutes.
Yeah, that's yeah, for me, I need to catch up a little bit more on stuff. So I'm a little confused, so this is like internship, that's like for OSU, right?
Yeah,
So, like,
yeah, it's for us.
they technically say on like the website, it's like for OSU like students.
I don't know, for undergraduate students, it's for undergraduate students.
So, intern-
I said.
Wait. Okay, I was looking at it differently. So internships at SOREC are available to local undergraduate and graduate students in Southern Oregon, comma, to OSU students, comma, and depending on limited funding via resources like OWRs. Yeah, I'm actually kind of curious about that specifically with the molecular biology.
Because I missed it, I wanted to try and find Stanford this year, but I missed the application date, so
Oh,
I'm just
dang.
gonna try next year.
Yeah. Looking at Stanford?
That would be my dream school.
Yeah, that's the thing, is Oregon.
Well, we're gonna get the Ford scholarship. so-
Ford, problem with Ford scholarship is it doesn't work, I don't, from what I
Does it
saw.
only cover for bachelor degrees?
No, I think it only covers for Oregon colleges.
That doesn't sound right, but.